Hello everybody. Today we are going to discuss probability distributions, and under probability distributions we are going to discuss the normal distribution. And in the normal distribution we will be discussing continuous distributions, and there are two types of distributions that we are going to discuss today. One is the T distribution, the other is the Z distribution, or which we call as the standard normal distribution. Now many of you may be familiar with the first picture on the top, or the first graph on the top, and there's another one at the bottom. And as the name says, the top one is the uniform distribution and the bottom one is the normal distribution. Now how do we get this shape? That's a question which actually keeps on pricking a lot of people. How do we get the shape of a uniform distribution? How do we get the shape of a normal distribution? In order to understand uniform distribution, normal distribution, probability distributions, you need to understand how these graphs or charts are constructed. So let's talk of the uniform distribution, and it would also serve as a small refresher. Let's take the case of a coin flip. When we flip a coin, there are only two possible outcomes, and that being a head and a tail. What is the possibility for a head and what is the possibility for a tail? They both have 50-50% chance, as we say. And when we convert this possibility and chance into technical language, we say that the probability of getting a head is 50% or half, and the probability of getting a tail is 50% or a half. So how do we make this distribution? We can simply make this distribution, and it's not very difficult to understand. Let's assume that I were to draw these two axes, the x and y. So I just draw a rectangle, and or a circle or a square, and I divide this into two, and they should be equal actually. Or I can actually use this tool. This is a better tool. It will help me. I can just draw this. Now you can see. So I've split this into two equal halves. Now the first one could be a head or it could be a tail. This could be a head and this could be a tail. So if I were to just put in the probabilities for both of them, for a head it's going to be half, for a tail it's going to be half. And if I were to sum the probabilities, that would be equal to 1. So in this case, there were two possible outcomes, head and a tail. So we have only two, what we call as bars. In this particular example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 possible outcomes. Let's assume that you roll a dice. So when you roll a dice, there are 6 possible outcomes. And those outcomes being 1, getting a 1, or getting a 2, or getting a 3, or getting a 4, or a 5, or a 6 on the face of the dice. Now all these events, okay, the event and their probabilities, associated probabilities, are 1 by 6. That is, the chance or the probability of getting a 1 on the face of the dice is 1 by 6. So is the probability for 2, 3, 4, 5, 6. They're all 1 by 6. They're all equal. When the probabilities are constant, and so we call such a type of distribution, when we draw a distribution, we call it a uniform distribution. So I'll just highlight this. So the probability is constant. It is not changing. The probability of getting a head does not change. Let's assume that you repeat this example, okay, or repeat this exercise over and over again. That means you flip a coin 1,000 times, 10,000 times, 20,000 times. Whenever you flip the coin, the probability of getting the head or a tail will always remain as 50% or half. It is never going to change. So when you flip it once, the probability is 50% for tail and 50% for head. When you flip it again, the probability of getting a head or a tail is again 50%. It does not change. So when we plot the distribution, and when we look at the distribution, we are talking in terms of the frequencies. So let's assume that you have flipped a coin 10 million times. So you look at the results and then you will plot the probabilities. I'll show it to you. If you hold on for a second, I have here in front of me an online coin simulator or emulator, if you would want to call it. So I can either click the coin, I can flip it, or I can click a button to flip it. So let's do the first thing here. I'll just click on this and I get a head. I can again flip it, I get a head. I can again flip it, I get a head. I can again flip it, I get a head. I can again flip it, I get a tail. I can again flip it, I get a tail. I can again flip it, I get a tails. So I can do this exercise 1,000 times, 1,000,000 times, and I can note down how many times did I get a head, or how many times I got a head, and how many times I got a tail. This exercise has already been done by this emulator. On the left hand side, you will see the global statistics. So out of nearly 10.5, approximately 10.5 million flips, I did some 5, 6 flips. They've all been recorded here. Similarly, others must have done it in the past, or they might be doing it right now. So the number of heads is around 5.2 millions. Similarly, the number of tails is also equal to 5.2 millions with very slight differences. So the percentage of heads obtained by this emulator is around 50.02%. And the percentage of tails which were obtained, the flips, were 49.98. What does it tell you? The theoretical probability of getting a head or a tail is the same as, or the empirical probability, empirical means with the experiment, the empirical probability of getting a head or a tail is actually the same as the theoretical probability, which does not happen in many cases. So we have just demonstrated we could do the same thing with the dice, we could do the same thing with a pair of dice, we could do the same thing with pair of coins, and we can do this exercise. The probability of an outcome is always going to be, or the probability of getting a head or a tail, or getting a 1 or getting a 2 or getting a 3 on the dice will always be uniform, it will always be constant. And when we plot this number, the number of heads and the number of tails, in the form of a histogram, when we plot this in the form of a histogram, which we did a few minutes back, it is basically the uniform distribution. Now, making a uniform distribution is comparatively easier as compared to a normal distribution. Now, we know how a uniform distribution, especially a discrete uniform distribution, gets its shape. And where does it gets its shape from? How do we make the uniform distribution? How do we draw it? It's very simple. On one side, you have the frequencies. On the other side, you have the outcome. So in the case of head and tails, you would only have two bars, head and tail, and the frequency would be 5.2 million and 5.2 million each. So that actually tells you that the probability is 50-50%. Now, how do we make a normal distribution? This is an interesting concept. It's something which is very simple, yet at the same time very complex. And many people find it difficult to understand how the shape of normal distribution comes about. So let us take an example. Let us say that you have been given a task, and the task is to go to a mall. We have taken the case of a mall because a large number of people come to the mall, and you will have a large population from where you can actually sample. So let's say I ask you to note down the height. Okay, I ask you to note down the heights of different people at random or randomly who are entering the mall or leaving the mall. So what you do is, I say that you take a sample of 1500 people, and let's assume it's a good and a big mall. So you have a lot of people coming in, let's say 5,000 people, 10,000 people a day. So you actually do this exercise and you note down the heights of different individuals. I mean, obviously, this would be based on your observation. So, what you can do is you can have some range. That is, you need not be very, very accurate. But if you think that there's somebody between 4 feet to 4 feet 6 inches, if you find one person like that, you note that number. That okay, one person, two persons, three persons, four individuals, five individuals, six individuals. So you can do it for all the people or the 1500 random sample that you have. Once you complete this exercise, let's say 1500, if you were to plot, if you were to make a histogram, how would your histogram look like? Would your histogram look like this? That people between 3 and 4 feet, you found that they were actually out of these 1500, 300 were actually between 3 and 4 feet. And when it came to the height of 4 to 5 feet, you found that again they were 300. Between 5 and 6 feet, they were again 300. 6 and 7 feet, they were again 300. 7 and 8 feet, they were again 300. No, actually, this is wrong because that would never be the case. What will happen is when you do a random sample of people coming in and going out of mall, and when you collect or when you note down the height of 1500 individuals, what you are likely to find is that you may find one or two or three or four people who are actually between 3 and 4 feet. Similarly, you may find there are a couple of people who are, 7 to 8 feet. But majority of the people would be around this height, which is 5 and 6 feet. So out of 1500, 900 people would probably 900, or even higher would be in this particular range. And between 4 and 5 feet, you will have very small numbers. Similarly, between 6 and 7 feet, the numbers would be small. But majority of the people would not be here or here or here or here. Majority of the people would lie between 5 and 6 feet. So when we make a distribution in such type of cases, they follow not a uniform distribution as we had seen in the case of coin flip. They actually would resemble something like this, that people between 5 feet 5 inches and 5 feet 8 inches are 500. People between 5 feet 9 inches and 6 feet are close to 430. So your histogram, your frequency distribution is going to look like this in a phenomena which, like when you are measuring the height of randomly measuring the height of individuals, or the weight of the individuals, or things like the blood pressure of the individuals. It is not going to be a uniform distribution. What do we mean by uniform distribution? That the probability of finding somebody who's 3 feet and 3 feet 11 inches is very small. It is not the same as the probability of finding somebody who's 5 feet 5 inches and 5 feet 8 inches. So this is the point that I'm trying to make. So each of these has a different probability. This has finding somebody who's between 7 feet 6 inches to 8 feet is very, very minuscule, the probability. But this wasn't the case in a uniform distribution. In the uniform distribution, what we have seen is that all the outcomes have an equal chance, or that is, their probability is constant and uniform. So that is why we have a straight line. But in this case, the different outcomes, these are the outcomes of finding people who are between a particular height. So these are the outcomes. All of these outcomes have different probabilities. And that is why we don't have a straight line here. So if you go to the next slide, you can see if we collect, even larger sample. Now in this case, a large sample is of, the country's population, and we have sampled around 15 lakh individuals, and we have plotted their height. So this curve, looks like to be a very beautifully, evenly balanced histogram. Sorry, not a curve, a histogram. And if we were to draw a smoothing curve, okay, which may look like this, so I'll take a pen. So if we were to draw a curve, the curve would look like this. I may not have been very accurate. Actually, the peak should have been a little bit up, but it doesn't make any difference. So it should look like this. Now, the important thing to note here is if I were to ask you to find out the probability of finding people who are between 5 feet 4 inches and 5 feet 7 inches, it's going to be very, very simple for you. How would you do it? You can simply add up all these numbers, find out the total, and the total is, we know it's 15 lakh. So 2.5 lakhs divided by 15 lakhs will give you the probability of finding somebody who's between 5 feet 4 inches and 5 feet 7 inches. But in the real world setting, we say that this is the normal distribution curve. And the curve, the data may not be for many of the phenomena that we were, or the phenomena that we are talking of, the data may not be like this. So you have all these vacant spaces, which I am just pointing out. So you have all these vacant spaces. If I were to ask you, please calculate the probability of not only that red area, but this particular area, which is now shaded. I'll just shade this. So this shaded area, what is the probability of this area? It's going to be very difficult because you need to know calculus to do it, because this is a curve. This is not a straight line. So here you have a curve and you need to integrate to get the area between 5 feet 4 inches and 5 feet 7 inches now. So we are lucky, which we'll come to in a few minutes. We are lucky that statisticians have given us something called as a standard normal distribution curve, where they have calculated and they have computed all the probabilities under the curve, and they have made a table which we call as a Z table, or it is called as a T table if we are using a T distribution. More on that in a few minutes. So let's move ahead. So we get a curve like this. This curve may be more peaked, and these tails, as we call them, may be less fatter. So it has more probability here. It has more. This could be more peaked. So this kind of curve is called as a normal distribution curve, and the curve is drawn over a histogram, as we just saw a few minutes back. So such a curve is called as a normal distribution curve, and as was the case with binomial distribution, which is sometimes called as Bernoulli distribution, or a Poisson distribution, which is called as a Poisson distribution, this is also called as a normal distribution, is sometimes called as a Gaussian distribution, and it is also sometimes called as a your bell-shaped curve, or the empirical curve. Now let's just look at it for a minute. You can have people who are short, but most of the time you will have people who are of average height. Once again, let me put it this way: the probability is about chances. So I ask you that wherever you are sitting or standing, or relaxing, or whatever you might be doing, just go out of your house, hostel, office, just randomly note down the height of the first three people that you meet. What is the probability of finding somebody who is 3 feet? What is the probability of finding somebody who is, you know, 8 feet? Very, very low, because you're not likely to meet somebody who's 8 feet. It could happen. It could happen because there are people who are 8 feet tall. It could so happen that you are so lucky that the first person that you meet is the person who is 8 feet, and the second person that you meet is the person who's 3 feet. It can happen. But that is going to be the rarity, because if somebody, just imagine that there are three or four people who are doing the same exercise, will they get the same kind of results? No. So let's assume that you in your sample, you had somebody who was 3 feet and somebody who was 8 feet. But that is a rarity because such people are rare. So What will happen is, normally when you will go out and when you will sample three people or three individuals, you will find that majority of them would be of average height, because the largest number is of is between 5 feet 6 inches to 5 feet 9 inches. So you're likely to find people who are of the national average height. This is the concept of a normal distribution. So normal distribution doesn't look like a uniform distribution. A uniform distribution has a straight line. In a normal distribution, you have the probability of finding somebody who's very short is very low. The probability of finding somebody who's very tall is again very, very low. The probability of finding somebody who's of average height is very, very high, because those people are the maximum in number. So that is the reason. So I hope this concept is clear to you and we can move ahead. Now, this is what the real world phenomena looks like. And if we were to draw a curve, we can say that this is a normal distribution curve. At this moment, it's a histogram. As soon as we draw that curve, we are talking of a normal distribution curve, and the area under the curve is 1. So the probability under the curve is 1. Always remember, the probability of any event is 1. So for example, when we flip a coin, so we have a head and we have a tail, and the sum of head and tail is 1. When we roll a dice, the probability of each dice, each outcome is 1 by 6. When we add 1 by 6, 1 by 6 6 times, it becomes 6 by 6, which is equal to 1. So the probability under the curve would always be equal to 1. Now, like I've been saying, in the real world, many natural phenomena are normally distributed. So you'll find people who are very short, most of them will be of average height. Some people may be tall, but people very tall would be a rarity. Same would be the case with weight and many other things, like for example, average commutation time. So there will be some people who will live close to the office, who find it very, very easy, and they will reach the office in 5, 10, 15 minutes. There would be some people who would reach their majority of the people would reach in an average time, and that average time could be anything. It could be, let's say for example, it is 45 minutes. There would be some people, who would be coming from very far off, but those would be a rarity. So when we have the average, when we talk of the average or the mean, we are going to have an equal number of the left hand side, or nearly equal number on the left hand side and nearly equal number on the right hand side. That is the property of a normal distribution. So many of the things in life are normally distributed. Now, you know that many phenomena are normally distributed, and that is the reason why normal distribution is said to be the most important probability distribution in statistics, because it helps us in many, many areas, especially in hypothesis testing, significance testing, if you want to call it, inferential statistics. So this distribution is a very popular distribution. It goes by different names. It goes by the name of a Gaussian distribution, the bell curve, the empirical curve. And why do we call it a bell curve? When we draw the curve, which fits the histogram, it actually, of a normal distribution, it looks like a bell shape. So that is why we call it a bell shaped curve. Now, if you were to look at this once again, let me explain this point once again. When we look at this curve, what are these? This 100, 120, what are these? This could be anything. This could be weight. This could be height. This could be any number. But what actually are these? This is 100 to 110, 110 to or 111 to 120, 121 to 130. So these are actually intervals. And what are these in this particular direction? This 10, 20, 30, 40, 50 are the frequencies. That means between 100 and 110, you found 5 things. The count is 5. Similarly, between 110 or 111 to 120, you found around 13. So these are the counts, and when you plot the counts or the frequencies, you get something which you call as a histogram. And when you draw this curve, you call it a normal distribution curve. Okay, so we can move ahead. Let's come to the types of distribution. The types of distribution, as I said, there are basically two types of distribution. One is called as the t distribution, the other is called as a z distribution. I'm not going to go into the history of the t distribution, but if you want to understand t distributions and the t test, you can refer to my earlier video. Now, the z distribution and the t distribution, they have similar shapes. But remember one thing, the t distribution is used when we have a small sample size. What do we mean by a small sample size? Again, let's say I asked you, I've given you an exercise where I ask you to go out, collect a sample, and based on that sample, predict the average height of an Indian. So let's assume that I've given the task to individuals. I give this task to individual number one, and I say, okay, you can collect a maximum of 10. Your sample size is going to be 10. To the other person, I tell him your sample size is going to be 100. What does it mean? That means the first person is going to only randomly look at the heights of 10 individuals, whereas the other person has an option of looking, or I mean, he doesn't have the option, he has been given the task, so he has to look at the height of 100 individuals. Now, it's very simple. When you are trying to predict the height of an average Indian based on a sample of 10 versus a sample of 100, you are less likely to be accurate. The individual who has drawn 100 samples, he is more likely to capture the natural variation which is present in the overall population. He's more likely to, you know, his sample is more likely to incorporate that. So, what does it tell us? It tells us one thing very clearly. It tells us that if the sample size is small, you will be less certain of predicting the actual height of the population, or or let's say the mean. It is the average height is the average mean. So if we were to make it generic, if we have a small sample, we are less likely to predict the mean of the population, and the population could be anything. It could be population of television sets or income, individuals, animals, it could be anything. So when we say that we have a small sample, we are more likely to be we are more likely to make mistakes in prediction, and that is the reason why we use something called as a t distribution if we have a small sample size. Similarly, if the sample size is big, we use something called as the z distribution. Now, what are the differences? We've already discussed the shape of a normal distribution. Both are t distribution is a normal distribution, the z distribution is a normal distribution. But the differences amongst them, the main difference is that if you were to look at this, the yellow one, as you can see, is less peaked, and it has, I should say, that the word that we actually use in statistics is that it has a fatter tail. So these are called as tails. So it has a fatter tail. That means you have a larger number here as compared to the one which is in black, or as compared to the one which is in blue, or the one which is in purple. If we were to relate this with our earlier example that we had taken of, people being short and tall. So what happens in the case of this black one? There would be very few people because the line is very, very flat here. Very few people here. But if we talk of this yellow one, we have a substantial number here because the histogram would be up till this height. And in this case, the histogram would be of this height only. So that would mean that we would have very few. The frequency or the count would be very, very few in the case of the one having a black line. Now, this has to do with your sample size. And I've just related this, that a t distribution is dependent on the sample size. Lower the sample size, the fatter is the tail. That means you have more uncertainty. And when you have more uncertainty, bigger is your confidence interval when we are trying to predict the mean of the population. What do we mean by all this? We mean that whenever we are trying to actually predict the mean, we never talk in terms of one particular number. We never say the average height of an Indian from my sample is 5 feet 7 inches. I will always talk in terms of confidence interval because my sample could be different from somebody else's sample. But since the sample is coming out from the same population, the values are likely to be close. So, for example, my sample, I have taken 100 people, and that sample says that the average height of an Indian is 5.7 inches. Somebody else takes 100 people, but they might be different, or some of them may be common. And he or she may come out with the answer saying that the sample height, the sample mean is 5 feet 6.5 inches. Now, who is right? Him or me? Nobody's right, nobody's wrong. Because when we are talking of prediction, one sample every sample, when we are talking of predicting the height of the population, we can never be 100% accurate. The only way we can be 100% accurate is when we take a census. So that means the entire Indian population, we note their population, we note their height, and we note the population which is close to 1.3 billion or even a little bit more low, higher. Then we take the average, we'll be 100% accurate. But what we are trying to do is we are trying to take a sample, we are trying to take a sample of 100 people, and based on this, we are trying to predict the average height of Indians. So we will always talk in terms of confidence interval. And the confidence interval is, we will say that, for example, we actually need to calculate it, but I'm just going to, illustrate the point. So this, I'm just going to say that the confidence interval is my confidence interval is between 5 feet 5 inches to 5 feet 10 inches. That means with the sample that I have drawn, I am predicting the population mean to lie between 5 feet 5 inches to 5 feet 10 inches. So this is a pretty wide confidence interval if you look at it. Because 5 feet 5 inches and 5 feet 10 inches, there are at least 5 inches in between. But let's assume that I had a bigger sample size. I would be more accurate because that sample size would be more representative. And then again, if I had a even bigger sample size, I would be much more accurate. So as I keep on, increasing to a certain limit, the sample size, my confidence intervals are going to become narrow and I'll be more accurate because my sample would be incorporating the natural variations which are present in the population. Okay. So when a t distribution, in the case of t distribution, the sample size is very, very small. And when the sample size is very, very small, the variation in the sample may be large. And because of that, what we do is, what we say is that the confidence intervals of when we use a t distribution are bigger. So we are less likely to be more precise in terms of, or more accurate in terms of predicting the mean of the population. But luckily, if the sample size is more than 30, it is what people say. It is what statisticians say. It is not sacrosanct. It could be 28, it could be 29. People generally say, the general understanding is that when the sample size is more than 28, 29, 30, the Z distribution or the T distribution starts approximating the Z distribution. Distribution and the color is blue, while for the red is magenta. For the Z distribution, it is magenta. So we can see, and you can see the Z distribution is more peaked, the T distribution is less peaked. Why? What do we mean by more peaked and less peaked? That means the standard deviation for the Z distribution is lesser as compared to the standard deviation for the T distribution. You need to know the concept of standard deviation. Standard deviation is the how far the spread is from the mean of the different data points. So that's what standard deviation tells you. So in this case, the standard deviation is lesser for a z distribution, it is more for a t distribution. And if we scroll down, we can simply see that the area under the curve, especially towards the end, or which we call as the tails, both the left tail and the right tail, we can see that the values contained or the probabilities contained in the tail is more for the t distribution and less for the z distribution. I've already explained the concept a few minutes back. I've already explained the concept that we use a t distribution when the sample size is lesser. When the sample size is small, we are less confident of our predictions, and a t distribution incorporates all these things. And when the sample size is big, we always use a z distribution. And we can now see with the simulator, this is a degree freedom of 3, and when we make a comparison, there's the t values and the z values for different alpha levels. But just forget, if you are not aware of the alpha levels and if you are not aware of the significance level, just look at the t value. The t values are all in the first row, and in the second row, first row in red are the t values, the second row in red are the z values. And if you were to make a comparison between the t and the z, you can see, if we can do it column wise, so the t value for 10%, the t critical is 1.6, while it for a z it is 1.28. Similarly, for 5, 2.5, 1.05, we can see that in all the cases the t value is more uh, as compared to the z values. So when we are calculating the confidence intervals, we have a formula where we estimate the margin of error, which we add and subtract to the sample mean, which gives us the confidence intervals. So the formula is the t critical or the z value multiplied by standard deviation of the sample under root n. So we can see that if the t value is more, the error would be more, and if the z value is less, which is the case, if we keep everything constant, if we make a comparison between t and z, we'll find that the t value is more, so this is more likely to increase the error term as compared to the z. So when we look at our point estimate and we add the errors or the error in, predicting the mean, so what will happen is that the confidence interval that we generate using the z or the z distribution, the confidence interval would be smaller, and the confidence interval for uh, the, the 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 t value, if it is the less, if the sample size is smaller, the confidence interval will be smaller. Now, if you look at this, if we were to change this, if we were to change this to, let's say, 5, please keep on watching these values. So I change this to 5, and as soon as I hit the button enter, automatically the values change. But you can see, as soon as this degree of freedom is 5, this these values, the difference becomes lesser. If I were to make it to 10, the difference is even lesser. If I were to make it to 15, the difference becomes even smaller. If I were to make it to now 30, the difference is very, very small. And you can see, if you are following the graph or the t distribution and the z distribution, they are almost the same. You can see there is an overlap, okay, and you can see they're nearly the same. So let's just go back to 15. We can see for 15 there is a difference. We can see both the lines. But when we move to 25, the difference is very, very small. When we move to 30, we can see the t distribution and the z distribution are nearly the same. And when we move to a sample size of 100, we can say that the t distribution and the z distribution become the same. And if you look at the values now, the values are also similar. The only difference is at the third decimal place, which is really not a meaningful difference. So we always tend to use, when we are talking of normal distribution, we always tend to use a Z distribution when the sample size is more than 30. If it is less than 30, we always use a T distribution. But the best part is, in an era of information technology and when the computers are so powerful, we don't need to, many of the softwares automatically, based on the sample size, they automatically decide on their own whether they are going to use the Z distribution or the T distribution without you having to tell them. So that's the advantage of softwares such as SPSS and many advanced softwares. So if the sample size is more, they will use the Z value. So it doesn't, and if you were to look at it the other way, we know that even if we were to use a sample size of 100, the T value and the Z value would more or less be the same. So as soon as the sample size becomes more than 30, the T and the Z values become similar. So whether you use a T value or whether you use a Z value, there's not going to be much difference to your overall or final, your estimate of confidence interval. So this is what we mean by a T distribution and a Z distribution. So as we have seen from the simulator, we know that as the degrees of freedom or the sample size moves towards infinity, which is it becomes large, the T distribution becomes a Z distribution, or the difference between T distribution and Z distribution becomes negligible. So in place of T, we can use a Z. It doesn't make any difference because the T critical and the Z critical would be more or less the same. Now, why the Z distribution or the standard normal distribution is so popular? The appeal has been enhanced by something called as the central limit theorem. The central limit, till now, what we have been discussing is that if your data is normally distributed, if you have a normal distribution, you can apply the you can use the concept of normal distribution, and you can apply the properties of a normal distribution if your data is normally distributed. There's something called as the central limit theorem, and the central limit theorem says, it has come out with something very interesting, and it's obviously a very old concept. It says that if your sample size is large, then it doesn't matter whether the data is normally distributed or not, because even if the data is not normally distributed, the means the means that you would be drawing, or the means of the data, would be normally distributed. I'll explain this with the help of a simple example. Let's assume that there's a large population of mice. So rather than human beings, this time I chose mice. So let's take there's a large population of mice, and taken down, we have taken a sample, and in this sample we take a sample of 5 mice, and this is a random sample. And when we look at the weight of those mice, we measure them, we weigh them, and we plot their weights, which you can see. So we have plotted the weight. So all these mice would have a different weight. Also, what we can do is we can take the mean weight of these 5 mice, would look like this, and this they would also have a standard deviation. We can calculate the standard deviation of these 5 mice. So we have a mean and we have a standard deviation. Now, if you look at the weights from the mean, you can see they are a little bit spread out. That is why you can see that the standard deviation is also a bit more. This is a simple concept to understand. If you don't know standard deviation, then you have to go back and study standard deviation. But otherwise, you can easily understand that you have 5 mice from a sample, you can calculate the mean, and then from the mean, you can calculate the deviations. And when you square those deviations and you divide them by the sample size, and if it is a sample, so it will be n minus 1, you will get the standard deviation. And that standard deviation is depicted here. Now, Let's assume that you take a sample, 5 samples, rather than one, which was the case earlier. You take 5 different samples, and obviously these samples are drawn at random. Now, this is the first sample, this is the second sample, and the weight of the mice have been plotted on this number line, or the weight line you would want to call it. This is the third sample, this is the fourth sample, this is the fifth sample. This is the fifth sample. So what do you see? You find that, as it is to be expected, the sample is not coming from a factory. Mice are mice. The mice is the weight of the mice is a natural phenomena. So you will have mice of varying weights. Some may be more in weight and some may be less in weight, but most of the mice would be somewhere in between, near the average weight. So each sample would have small variations, as you can see. Now, if we were to plot the means of each of the sample, so let's say we calculate the means of each of the sample. So this is the mean for the first sample, this is the mean for the second sample, this is the mean for the third sample, this is the mean for the fourth sample, and this is the mean for the fifth sample. And not only the mean, we also plot their standard deviation. So the sample which has lesser variation will have lesser standard deviation or smaller standard deviation, or the samples which have a lot of variation will have more standard deviation or a bigger standard deviation. But the interesting point that you need to know, irrespective of your standard deviation and how the sample was, you'll find that all the means are very, very close together. They are clustered around a central value. So your if this was your population mean, if you were to draw an imaginary line, the rest of the means are very close to the population mean. Now, like a natural, since it's a natural phenomena, irrespective of the fact, where what your sample was, irrespective of the fact what your sample was, if you were to take multiple samples, with 100 samples, 200 samples, 300 samples, 400 samples, even if it was not a natural phenomena, okay, let's say it was something like a coin flip, or roll of dice or whatever, you will find that the means would always be close together, irrespective of the individual variation in the sample. The all these samples, sample 1, sample 2, sample 3, sample 4, and sample 5, there are variations. And that is why you can see the standard deviations are different. But apart from that, forget the differences in the standard deviation. If you look at the means are very close together. So if you plot 100 means, the 100 means you will have more, they will be much more closer. Some would be close, some would be a little bit far off, depending on the sample that you have drawn. And then you will have a sample where you will have all 5 fat mice, and one sample could be where you have 5 underweight mice, and then you could have different combinations. So but those would be far and few. So if you were to plot them on a number line and forget about the individual samples, but if you just to take the means, it would look something like this. With one or two, samples coming here, which would be very fat mice, and this could be very thin mice, so they would come here. But majority of the samples would be very close together. And remember, once again, this would start resembling our histogram. So the shape would start resembling a histogram. This is what the central limit theorem says that. And because of this central limit theorem, we know that if the sample size is large, we need not even bother about whether the phenomena is a natural phenomena, or it is normally, or the sample is normally distributed. We need not even bother about that. We need to only bother about one thing, that is, the sample should be large enough, so that the means of the plot of the means becomes a normal distribution curve. So areas. Now, like I was saying, most of the empirical distributions are not normal. They this is the income distribution for 2020, and you can see it is skewed. and the data is skewed. What do we mean by this? This means that if we were to plot the mean, this is the 50%, people who were earning very less, or people who had a very, well, majority of the people were earning 50%. If you were to look, there are very few people who were earning $80, $75, $70. Numbers were there, but there were very few. But majority of the people were on the left hand side. So there were a lot of people who were earning less than 20 or $15 or $10 or $5. But if we were to draw samples, okay, if we were to draw samples and then we were to plot the mean would become something like this. The sampling distribution of income would resemble something like this. Okay, and it says that the sampling distribution of mean income over many samples is normal. So that if we have a large number of samples, so the sampling distribution is going to become, it's going to be a normal distribution. So this concept makes things easier in terms of comparison. Now, we'll just summarize the central limit theorem. The central limit theorem says that if we repeatedly draw samples from a population and calculated the mean of a variable, what could be that variable? It could be height, it could be income, it could be any variable that we are interested in. It could be roll of two dice, the sum of two dices, the roll of three dices, the sum of three dices, which is actually a uniform distribution. What we would get is that we'll get a normal distribution. The means will be normally distributed. So this is the central limit theorem. Now, what are the properties? Let's first understand the properties of a normal distribution. So the normal distribution, of which has a curve like this, the properties is that 50% of the 50% is on the left hand side and 50% on the right hand side. Now this 50% could be the probability, depending on what is your reference point. So if you're talking in terms of probability, this part, the left hand side of the mean contains 50%, and the right hand side also contains 50%, and they are mirror opposite of each other. They're symmetrical. And in this, the mean, median, and mode are equal. You may ask me this question: how is the mean, median, and mode equal? If you look at this, here we have a peak, and just related with the histogram, what is the mode? The frequency which occurs the most. So here we have the highest frequency here. So this is going to be the mode. And how is this? How do we decide a median? Median is one which splits the data into two equal halves. So it is the mean which is also splitting the data in two equal halves. It is the median and the mode. So we say that the mean, median, and mode are equal. Area under the curve will always be equal to 1. So the probability under the curve will always be equal to 1. The percentage will always be equal to 100, because we're talking in terms of percentage. Now we are talking of this left hand side and we are talking of the right hand side. Even though we see that the lines seem to be touching, but they are not in reality. This is going towards infinity, positive infinity. This is going towards negative infinity. Why? Because this is a continuous distribution. The values that we are talking of are continuous in nature. That is, the variables that we talk of, they are continuous in nature. For example, we can have, just we were talking of heights, so it could, or we were talking of weights, so somebody could be of 1.111111 kg, and there could be another person who would be of 1.11112 kgs, and so on and so forth. So it's a continuum from minus infinity to plus infinity. The area under the curve will always be 1. We know that the probability is always 1, and when we are talking in terms of percentages, it's 100%. Look at this. Sorry, there are three normal distributions. There's the one in green. You can see it is very flat. So we call this as platokurtic. And this is very peaked. It is called as leptokurtic. Okay. And this one, is in between. Now, when they are very spread out like this, it indicates that the standard deviation, this has a, the one in green has a standard deviation which is more than the one in blue, and the one in red has the least, or has the smallest of the standard deviation, because most of the values are clustered around the mean. So this is the property of a normal distribution. If you have a lot of variation in the data, you are likely to have a, normal distribution which looks like this. Whereas if the data is very close to the mean, your standard deviation is going to look like this. I'll give you another example. If we look at the height of adult males, we have a lot of variation. Because if you were to talk of it, we have a lot of people who may range from 55 kgs, and you will find quite a large number of people from 55 kgs to probably 90 kgs, adult males. Then you would have extremes. But if you talk of newborn babies, most of the babies would flow very close to each other, would weigh very close to each other. So if somebody is born at, let's say the average weight is 2.8 kgs, so you will have most of the babies around this particular weight. So that means the standard deviation, if you were to make a normal distribution curve for newborn babies, it's likely to look like this, where the standard deviation is very small, so the variation is very less, so you will have a normal distribution curve which looks like this. Whereas in the case of an adult male, it's going to look like this, because the variation is much more for adults as compared to the babies. So different standard deviations with and different normal distribution curves with different standard deviations can be compared. Now, what is this comparison and what is this standardization? This is something which I'm going to discuss in a few minutes. Okay. Now, just think, uh, of the fact that if we want to measure ourselves, okay, or if we want to measure something, let's say this, the mobile phone, and we want to find out the length of the mobile phone or the width of the mobile phone, what do? We use a small scale, which it's usually a centimeter scale with inches on the other side. Now, it has a zero, and from that zero we can, that's the reference point, and we measure the mobile phone. So some mobile phones could be 7 inches, some mobile phones could be 4 inches in size, some mobile phone could be 6 inches in size, some mobile phones could be 5.5 inches in size. So what are we trying to do? We have a reference point, and we are comparing ourselves with the reference point. If you are talking in terms of centimeters, the same thing could be, the reference point will be a zero, the starting point, but but the centimeters will be different. The unit is different. The interval would be different. So what I am trying to say is that we are lucky that we have only two or three popular systems of measurement. By the way, if you go to rural areas, you have many things like biswas and guz. Guz is yard. Biswas and guz and chota guz, bada guz, and there were a lot of other things. So you had different, you have, so just imagine, when we are saying of a normal distribution, for every sample that you have, it will have a normal distribution, right? And if it is normally distributed, if the data is normally distributed or it's a large sample, it will have is normal. If it is a normal distribution, it will have a certain mean and it will have a certain standard deviation. Now the problem is to compute values and to compute probabilities and to compute the percentages under the curve. It's going to be a nightmare. It is just like everybody having their own scale for measurement, so there would be no uniformity. Everybody would talk in their own terms. So that is where the concept of standard normal distribution comes in. And a standard normal distribution is a standardized normal distribution which has a mean of 0 and it has a standard deviation of 1. Now what you can do is you can standardize or you can make a comparison of your normal distribution with the standard normal distribution, because the standard normal distribution has certain properties, and those properties I just explained to you in a few minutes. It's a you actually have a mean of 0 and a standard deviation of 1, and the area contained between plus minus 1 standard deviation is close to or approximately 68%. An area between minus 2 and plus 2 plus minus 2 standard deviation is approximately 99%. And the area under plus minus 3 standard deviation is 99 point, approximately 99, 99.7. Everywhere there are some points. Okay, so I'm just talking in approximate numbers. So what we can do is we can take any normal distribution and convert it to the standard normal distribution. This makes life very easy because we don't have to compute, these the area under the curves for our distribution, because if everybody starts calculating, it's going to become a nightmare. So what the statisticians have done is they have calculated the areas, they have a standardized curve, and they have calculated the areas, and they have given it to us in the forms of either a t table when we are talking of a t distribution, or you know in the form of a z table, the z distribution. Today, computers, with the advance in computing power, computers and computer technology, and the softwares, you don't even have to remember the Z values. The software computes it automatically for you, as long as you tell your confidence level or your significance. So if you tell either of these, the software will compute it automatically for you without you having to look at the table. So what happens? A normal distribution can be standardized as a standard normal distribution. That means you can make a comparison with your distribution, with your mean, with your standard deviation, with a standard normal deviation distribution. So let's look at this. The standard normal curve or the standard normal distribution, this doesn't touch, it goes towards minus infinity, this goes towards plus infinity. The mean mu of the z distribution is 0 and the standard deviation is 1. Area under the curve will always be 1. This is again important. 50%, since they are mirror opposite, this side, the one in red and the one in white, they are mirror opposites of each other. So area under this side is 50%, the area under this side is 50%, the probability in this side is 50%, the probability on this side is 50%. If you are talking in terms of population, 50% on this side, 50% on this side. This is split into standard deviations and the percentage of probability or the population that is contained in them. So between one standard deviation, 34%, plus 1, minus 1, 34. And when you add them up, it is approximately 68. It is 68.41, but approximately it is 68%. On this side and this side, between minus 1 standard deviation and 2 standard deviation, the area or the probability or the percentage is 13.5 and 13.5. And between 2 standard deviation and 3 standard deviation, it is 2.5% and 2.5%. This 2.5% and 2.5% you all need to remember, because this is the most common significance level when we are talking in terms of hypothesis testing. So the area, if you were to total all these values, it will come out to be 1. Now, in this, the standard deviation has been split into 0.5. Everything remains the same. The only thing is there are finer splits. So if you want to use this, you can use this. But generally, most of the distributions that you will see only have or only show. It is not that you have to show. They only show for illustrative purposes that 1 standard deviation away, 2 standard and 3 standard deviation away. That's how it is shown. So that's the trend. It's not that it is right or wrong. So on a scale, you have 1 centimeter, and then you have small lines. No, it is not written on those lines that this is zero point 0.1 centimeter and this is 0.2 centimeter, it is 0.3 centimeter. You can come across some case where it might be written, but what is the trend? You have 0, and then you have a bigger line for 0.5, and then you have 1 centimeter, and again for 1.5 centimeter the line is slightly bigger, and then you have the intervals. So that is how it is. So this is just a convention. So between minus 1 sigma and plus 1 sigma, 68.26%. Between 2 sigma, minus 2 sigma and 2 sigma, the area or the probability under the curve is 94.44%. And between minus 3 sigma and plus 3 sigma, that is 3 standard deviations away, plus minus on both sides of the mean, you have approximately 99.74%. This has interesting applications, okay, for understanding the concepts. It has interesting applications. If you look at this, this is what we call as the probability distribution curve. We all know that 50% is on this side, 50% on this side. This has been broken up. But what you can see is, even though they are mirror opposites, it is 15.87, but here it is 0.8413. Such a curve, it's the same thing as the previous, but what we are saying is, when we talk of probability, we talk of cumulative probability. So if we were to measure the probability here, it is between minus 4 to minus 3. We'll say the area under the curve is 0.0013. Okay. The area from minus 4 to 2 is this area plus this area. So you add this probability to the probability of this area and it becomes 0.028. These two added becomes this. These three added becomes, so you keep on adding the probability. So the probability, you compute the probability, it is 0.013, 0.0013. You compute this probability and add to this becomes 0.0228. Similarly, you compute this probability and add to 0.0028, it becomes 0.1587. You compute this probability and you add this, it becomes 0.5. And so on and so on, which we saw a few seconds back. Here, we saw this. So we keep on adding all these and ultimately it will become 100%. So the convention is to start from this side saying 0 and 100. Okay. So in reality, what do we have? In reality, we actually talk in terms of, minus 3 standard deviation away to plus 3 standard deviation away, which is 99.7%. So, but we know that the area under the probability was always going to be 1. So we always talk in terms of minus 3 standard deviation away, plus minus 3 standard deviation away. As a researcher, as an academician, or as people who are using these normal distribution, we don't consider values beyond minus 4 and plus 4, because the number of such elements in the population, or the number of such things being there in the population, is very, very, very small. It's just like saying that somebody is 10 feet and somebody who's 2 feet. So we just tend to ignore them because majority lies here. So we are always talking of the majority. We are always using this normal standard distribution curve to predict, so this is the cumulative probability, and you can see, so 0.0013 plus 0.024, which is the probability of this, added, this becomes this. Probability of this is 0.1359, add this to 0.028, this gives you this. Similarly, from this side. So the convention is that we say 50% is on this side, 50% on this side, but we keep on adding as we move towards the right, and that's why we call it and that's the reason why we give it a name called as cumulative distribution, CDF function, cumulative distribution function. Now, before we go ahead, I would just want to give you a simple example. Let's assume that you have a normally distributed population. Okay, how do we use this? Let's say you have a class, and in your class, it's a math class, and the average score that has been obtained, or the average score is, let's say, 90. Okay, or let's say 80. To make it much more simpler, I will use the pencil and I'll say the score is 90. I will put this 90 here. I'm comparing. I'm making a comparison. The score is 90 and with a standard deviation of 5, or I'll make it even more simpler. I will say it's 80. Okay, with a standard deviation of 5. What does it mean? It means if I were to add 5 to this one standard deviation away, this would become 85. That is what the normal standard distribution curve says. It says you have to place yourself. This is your reference point. So your 0 becomes 80. So this 0 is my 80. And this one standard deviation is plus 1. So in my case, my standard deviation is 5. So this becomes 85. This becomes 90. And this becomes 95. And this becomes 75. And this becomes 70. And this becomes 65. Okay. So this is my normal distribution with the vis-a-vis the standard distribution that we have. Now, if I were to ask the question that how many students scored between 70, what is the percentage of the students scoring between 70 and 90? So we will use the standard distribution curve and we can simply say that the students from 70 to 90, this is 2 standard deviations away. We know 95% of the people will be 2 standard deviations away. So we'll say that 95% of the students fall between 70 and 85. Okay, 70 and 90, sorry, 70 and 90. We'll say 95% of the students have obtained marks which are between 70 and 95. How many students obtained marks between 75 and 85? We'll say that, yes, we'll say 64% of the students. So now if we know the total population, very simple. So if we know the total number of students, let's say the total number of students who had given the exam are 70,000. The total number of students who have given the exam are 70,000 and we want to know the exact number of students who have scored between 70 and 85 or 70 and 90. We can simply multiply the area or the percentage under the curve and we can multiply it with 70,000. So for example, we know 2 standard deviation away, the percentage is 95%. So 70,000 into 0.95 or 95% of 70,000 will give us the total number of students. So that is how a standard normal distribution curve is used. It makes life very, very easy for us. So in the next part of this video, we will be discussing some examples and we'll see how normal distribution curve can be used. So this was basically to explain the concept of normal distribution, the t distribution, the z distribution, how these curves are actually made and the concept of the probability contained under them. Thank you.